Okay, just ping me if you can see the screen. Is it visible?
Yeah, we can see you.
Yeah. Okay. So let's go here. This is day 7, I guess. No, so day 7 was the expectation value. This is day 8. In previous one we learned how to calculate the expectation value of an operator, let's say x. So if you have a like a state psi, so this expectation value uh, can be found in a matrix form like this, right? Taking x as some n cross n matrix, your psi as n cross 1 matrix, and your psi will be psi conjugate transpose, and that will be 1 cross n matrix, right? So this is what we learned in the previous class. So now what we will do, we will try to do this expectation value of an matrix and decompose it into the Pauli's matrix, the psi x, psi y, and psi z. Psi x was something like 0, 1, 1, 0. This was 0, iota, sorry, minus iota, iota 0, and this one was 1, 0, 0, minus I. Oh, sorry, minus 1. Okay. So we would try to decompose this thing into this and use this one, as we can. I have told you that we can like the quantum computer. What can I say? Observes in uh, like what's it called? Eigenvector of this form, like 0, 1, and 1, 0, right? This form. So the quantum computer observes the state in these two state vector, and it's the eigenvector of this control sigma z. Okay, so this is the overview. So now let's try to do it. So if we have a matrix M, let's say to the power n cross to the power n. So it if it's Hermitian, what's Hermitian? M is equal to M conjugate transpose. That's if this condition satisfies, then it's Hermitian matrix. Or okay, so if we have a Hermitian matrix, it's proved that it can be decomposed in a form of, let's say, A. Let's erase this one. It can be decomposed in form of A identity of the same order to the power n cross to the power n plus B sigma x sigma x. No, let's not call this one sigma x. Let's do it in a summation way. Okay, summation uh, I summation j dot summation and I guess this will continue n times, and then there will be sigma x, sigma y, sigma j, something like this, n times. This should be sigma I. So if we do this one in like just 2 cross 2, 2 cross 2, M is, let's say, a 2 cross 2 matrix. Well, okay, so what does this say? Okay, what does this say? That all the possible combination of sigma x, sigma y, sigma z, C1, let's say C2, sigma x, sigma y, all the possible combinations till n will be considered. Right? This will be sigma dot 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 something. Okay. So identity of 2 cross 2 matrix, 2n to the power n to the power n matrix with a constant a, and in summation of that, all the possible combinations of these three these three Polis matrix n times, we can find a, what can I say, decomposition of this matrix in this form. Okay, so if we have a, let's say, 2 cross 2 matrix, that m is equal to 2 cross 2 matrix. So for 2 cross 2 matrix, we can say that n is equal to 1. So it can be decomposed in A identity 2 cross 2 plus D sigma x plus C sigma y plus D sigma z. For, let's say, m is equal to the power 2 cross 2 to the power 2, say 4 cross 4. Okay, so for it would be decomposed in A I 2 cross 4 cross 4 plus, let's say, B sigma x sigma y plus C. I'm writing down it here. Okay, sigma x plus D sigma x sigma z dot 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 dot, all the possible combination of these two, some constant, let's say di sigma z sigma z, something like this, all the possible combination of these two. Okay, so there will be in total we have two sets, right? These two. This can be also written as I2 cross 2, I2 cross 2, right? Tensor product. So what can we say, that these has four choices. These has four choices as identity sigma x, sigma y, and sigma z. So there will be 14 possible combinations. Sorry, 16 possible combinations. So these are 16 possible combinations. So we won't talk about this 2 cross 2 to the power n cross 2 to the power n thing. Right now we will only talk about 2 cross 2 matrix. Okay, so let's assume that you have a m which is Hermitian. Let's say, what can I say, 1 1 2 2. It's a Hermitian, right? M conjugate transpose will be 1 2 2 1, right? So I say that this can be decomposed in that form. So let's try to do it. You can see that our identity kind of done in this way, 1 1. So taking out 2 cross 2 identity, then we are left with 0 0 2 2. And if you can see, this is 2 into 1, right? 2 into sigma x. So 2 cross 2 plus 2 into sigma x, right? So this can be done for any Hermitian matrix with a like, it can be decomposed in these forms. Okay, so now we will, like, say that it's a random matrix is A identity plus, take it to be 2 cross 2. Okay, so B sigma x plus C sigma y plus D sigma z. Okay, so we'll work with this, taking a arbitrary 2 cross 2 matrix. We'll work with it. Okay, so to find the expectation value of this m, we need to have a psi, right? And with the variational principle, that thing that I showed you, that it will go to the least possible expectation value of that m, the algorithm thing. Okay, so I told you that we are looking for minimum eigenvalue. right? And it can be found using the algorithm that I showed you, like a rough example of algorithm. We will talk about that algorithm in next class, okay, in the coding. So let's assume that we have an algorithm. And what does the variable principle says that if you have any algorithm, the m expected will be always be greater than m actual, like the m minimum. Okay, so we won't be getting the actual this thing. We will be trying to get as close as possible. Okay, as close as possible. So so we have a m and we want to minimize this thing. So we need to find a sigma such that it minimizes this thing, right? Because your m is predefined, so only thing that we can change is our sigma. So we need to find a sigma, sorry psi. So we need to find a state psi such that our this thing is minimum. Okay, so first thing we need to do is how to calculate this expectation value given a like given a specific psi. So let's assume we have been given a specific psi. Then the second step will be finding the m. Then after that we will be changing the psi, like changing a psi. Then we will seeing is it minimum or not, or is it greater than the previous one or not. So right now we will be doing only this step. If a psi is given, how to find the expectation value of it. Okay, and finding the minimum, the algorithm thing, we will do it in next class. So the first challenge we get is that our 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 quantum computer can only measure the state in 1001 state, right? That's in Z basis, right? So so we can't just take m and put it in the circuit and get all this. That's why we need to decompose in a form that it can be measured in z basis. Okay, so we can find this thing, but we need to find this thing. Okay, so we need to have a decomposition such that this m can be written in a form of this thing. So we use this. M is equal to our A identity, then plus B sigma x plus C sigma y plus D sigma z. Okay, so for this z, we can just measure it in the direction like up or down. For identity, it's same. Like identity doesn't do anything, so this sigma slash sigma will be equal to 1, right? As I told you that this correspond to psi transpose conjugate transpose, and this psi dx, and this one is your expectation value. So identity won't change it, and we know that psi is equal to 1. So this will be equal to 1 as our probability along this, like, should be 1. So this is 1. We know we can measure in that direction. What about sigma x and sigma y? So we can do a thing in where our sigma x, sigma y, sorry, this is what we want, right? But we can only measure in z direction. So we can do one thing where we transform this thing. Let's say sigma x is 0, 1, 1, 0. So if we find a like transformation such that a matrix A into Z into A transpose is equal to sigma x, then what we can do is we can write sigma x is equal to psi A dagger Z A psi, and then we can say that this psi A dagger Z A psi, this is our new psi dash. Okay, we can say that this is now our new psi dash, and we can say psi dash Z psi will be measured. This is still equal to psi x, but now we can measure it in this direction. So changing our state with some values like this a matrix, we can make our circuit measure in z direction, but it will be actually measuring in z direction, like transforming in a bit, so that we can take the z basis and move it along the x-axis. Okay, so how can we do that? A transpose z h, sorry, a, this is your x. Okay, so this is 1 minus 1 0 0. Let's write this thing
Bhaiya,
also. Okay,
excuse
so
me.
this is, yeah.
Uh,
Huh?
in the average value of sigma x, it will be psi dash z psi dash or psi dash z psi.
हाँ क्या इसमें?
इसमें ये psi होगा या psi dash होगा?
Oh, this one will be side. That's all. This one we transform it in a way like it should be side. Okay, I wrote it in that way. Sorry for that. Okay, so if we see it here, and we know that A transpose is equal to, sorry, A inverse. Okay, so what we can do is just write it here. And then we find out that A is nothing but equal to 1 by under root 2, 1 by under root 2, 1 by under root 2, minus 1 by under root 2. And if you remember this matrix, you can just say that it's a Hadamard gate, like the Hadamard 2 cross 2 matrix, right? That's 1 by under root 2, 1 1 1 minus 1, right? So what we can say, that if we have a psi coming through a circuit, and we just apply a H gate and then measure it along z direction, then it's similar to measure psi z direction, x direction. It's similar to this, okay, as it gives us the same result. So we got our psi z as usual, like just you have a psi state, then just measure it in the z direction. We got our identity. It shouldn't be done, as it's just it's just one. We got our sigma x y, sorry, x. That's psi should be transformed as h psi, and in circuit form, if psi is coming, then just put a Hadamard gate, and then measure it in z direction. For for sigma y, it's a bit complicated. Like you have minus iota, iota, and 0. So I won't be calculating this one right here, but I will just be stating it. Okay. So uh, this one can be written in sigma y in a matrix form. Matrix form can be written as rz rotation z axis by pi by 2 multiplying h matrix z matrix h matrix then rz minus pi by 2. It's a bit complicated, so I won't be doing it here. It would take me like 10 or 15 minutes. So I will provide with this how I find this in like a short video or something. Okay, so this is the decomposition of sigma y in terms of z. Okay, so this is how it can be achieved. So we can just say that if we have a psi, then if we multiply it with this h rz minus pi by 2 and then psi, transform it in this way and call this our psi dash, then we can measure y in y direction while measuring in z basis. Okay, so this thing is just like if you have a 2 cross 2, let's say sorry, two-dimensional state, and only one observer looks at this state. Okay, like looks in this direction, and you want to measure a particle here. Okay, it's just a vague representation. Okay, so if you want to measure a particle here, then it won't say that it will say that it's in at zero place, but it won't say that where it lies in x-axis, right? So but if we like transform it in a way such that this is x and this is y, if this becomes y and this becomes x, and our the observer is still looking in this direction, so it can just say that it's at like say 2.5. Okay, we can measure it in x direction as well. So it's just like that. We are just rotating our sigma our state in a way such that we can measure it in the y direction. Okay, so this is the matrix decomposition of that. And how we do it on circuit, we do it in a this way. If the psi is coming, then we apply our gate, that's rz pi by 2 minus pi by 2, then a h gate, and then measure in z direction. Okay, so we got our m. We know that sorry, we know that our m can be decomposed in a way like this: ai plus b sigma x plus c sigma y plus b sigma z psi, and we know that it can be taken apart as if we see it as an integration, we can just psi a plus b psi, then we can just say psi a psi plus psi b psi, right? Integration, we can do this thing. So we can just say that this is ai psi plus psi sigma x psi sigma z psi. Okay, this thing. And as we can take a constant out of the like integration, we can do it here also. A, we can just write it as I, as this is in a form. We can say that it's x, taking b we can say that this will be transformed in a psi dash, and then your z, then psi dash. Let's call this psi double dash, z psi double dash plus psi z psi. Okay, so we can do it in this way. So we can measure all of them, like say psi dash. This is h dot psi, and this one is psi double dash is equal to your this thing, this one, h dot rz minus pi by 2 dot psi. Okay, so we now know how to decompose a matrix in a form of Pauli's matrix. We know we can do this thing. We know that we can change our state in a form that we measure in z direction. But now let's see how to measure actually in z direction. Okay, so if you have a psi z psi, what will happen? And we are talking about 2 cross 2 matrix. Okay, so that's 2 to the power 1, that's 1 qubit, right? So 1 qubit has 2 to the power 1, that's 2 state, right? So for a fully entangled, sorry, fully superposition state, we can say that it's like something like a 0 plus b 1, right? Psi can be in this state, arbitrary state. Psi can be in arbitrary state with of this, where a square plus b square is equal to 1, or we can say a mod square plus b mod square is equal to 1. Okay, to get this thing, probability is equal to 1. So we can just say psi z psi is equal to a, this thing is a psi z a, not this way, we can write it this way, a 0 plus b 1, right? And then we can just say psi z, if z is applied on 0, this is 1 0 0 minus 1 applied on 0, it will give 1 0, right? And if we apply 1 0 0 minus 1 on 0 1, we will get minus 0 1. So we can say that it will be a 0 minus b 1. Now taking it apart, we have here a transpose 0 plus b conjugate transpose 1. Okay, so this z will disappear, right? Because we just multiply the z matrix with this thing. Okay, and in second we got a 0 minus b 1, and this thing will be equal to, why I'm writing, okay, so it will be equal to a transpose 0, then a transpose a 0 0 minus a transpose b 0 1 minus b transpose b 1 0, sorry, no, first 1 1, and then this one into this one plus B transpose A 1 0. But we know that 1 0, if we do this 1 0 0 1, this will be equal to 0, right? This into this plus this into this, so this will be 0, and with the same logic this will be 0 as well, as 0 1 or 1 0, this will be 0 as well. Okay, so we are left with taking psi is equal to a1 a0 plus b1. We are left with z, sigma z, sigma z, sigma. We are left with b, sorry, a transpose a minus b transpose b. Okay, so we can see that this one is the probability of state being in upstate, sorry, downstate, being in zero state, and this one is probability of state being in upstate, and we know that a transpose a plus b transpose b is equal to 1, right? So we can say that psi z psi is equal to probability of this 0 minus probability of 1. So this is our result for expectation value of z for a given sigma. Okay, so if we have a sigma and we run a circuit and measure it in the z direction, and we get like we run it like 1,000 times, and we get something like 700 times we get 0, and 300 times we get 1. So the expectation value of z will be equal to 700 minus 300 by 2, sorry, by 1,000. That's equal to 0.4, right? So this is our expectation value of z. Now if we minimize this, if we minimize this z expectation value of z using some algorithm, we will get the minimum expected value of z that will be equal to that would be equal to the minimum eigen value of z. Okay, that's actually -1. So if we have a state psi that's 1 0, not let's say 1 0, sorry, 0 1, then if we do this thing, we can directly see that if it's in a one state, totally in one state, this will be 0 minus 1,000, and this will be -1, right? If our psi is 0 1, then expectation value of z will be -1. This is the lowest we can get. Okay, using this one, like we can't get any lower than this, so we can confidently say that this one will be the least minimum least value of this uh, least eigenvalue of a operator z with a matrix 1 0 0 minus 1. So we found that z can be expectation z can be written in this way. Okay, so now what we do, is try to write the this one. What was it? Yeah, designer. Yeah, this one. This one, right? We know that this will be equal to 1, so we can just write a1 a into 1 plus the second, taking the d1 first, we can write d. You can write d probability of 0 minus probability of 1 of that state psi, specific state psi, taking as is psi and psi, then plus d probability of 0 minus probability of 1 of state psi dash, the state psi, plus c probability of 0 minus probability of 1 of state psi double dash, right? As this one was also equal to psi dash psi, this one was equal to psi dash x, sorry, z psi dash, and if psi z psi is equal to this, then psi dash z psi will be equal to this. Okay, we can similarly say that this thing. Okay, so we got this. Now, how to implement this thing? This is the base. This is the main thing I wanted to get to in this class. That if we have a m, that's Hermitian, like m transpose conjugate transpose is equal to m, then we can write it in a form that can be used by a quantum computer to find the minimum value of that expectation, right? So we can we can calculate this using quantum computer. Okay, so we can find this using quantum computer. Now, quantum computer itself can't like optimize it. Like, what can I say? It can find the probability, but it can't optimize the size state. So we need classical computer to do that. Change psi a bit. See if the new this expectation value of m is less than that or greater than that, and work on that. Okay, so there are multiple number of optimization algorithm, like Covila, like gradient descent. The basic one is gradient descent, where we look for the minimum, uh, like the lowest health. Okay, so there are a number of ways that one can optimize this thing, but this is the basic of all. How to get the expectation value of m using quantum computing. Okay, so I will try to uh, calculate this thing using a quantum computer in next class, or should I do it here and now? If you want, I can do that. Hello, should I leave? Actually, it's 1 hour, so maybe I should do it tomorrow or in the next class.
Yeah, that seems fine.
Yeah, okay. So let me write it in clearly. This uh, if psi is given uh, with m in same order, we can calculate expectation value of m, expectation value of M using quantum computer with use of decomposition in all these matrices. The formula is given by M is equal to A. Next, uh, M is equal to A I plus B X plus C Y plus D Z and sigma dash is equal to H dot sigma double dash is equal to H dot RZ minus pi by 2 dot sigma. Our expectation value of M will be equal to A plus B probability of 0 plus minus probability of 1 with the state psi dash plus C probability of 0 minus probability of 1 with a state psi double dash plus D probability of 0 minus probability of 1 with a state. Okay, so this is our formula, and I will use this one to calculate the minimum value of yeah. So this is the formula I will use to calculate the minimum eigenvalue of a matrix. Okay, so for now